Hello, my name is Andrei Orshula. I'm a PhD student from the Space Robotics Research Group at the University of Luxembourg, and today I will present the approach of the SpaceR team used during the Robot Air Hockey Challenge 2023. So let's dive straight into it by looking at the agent in action. Here you can see our agent playing against itself inside the simulation environment provided by the organizers. Our focus was on using learning-based control methods that are capable of autonomously playing the full game of air hockey with a single policy. And as you can tell by looking at the playthrough, this results in a very dynamic behavior of the agent. Although domain-specific knowledge can be valuable, we do not employ any handcrafted behavior or priors within the controller itself. Instead, our agent learns solely from sparse rewards while incorporating self-play to iteratively refine their behavior over time. Out of the possible techniques that can be used to directly optimize a single policy capable of playing air hockey, we decided to focus on reinforcement learning as an approach for learning decision-making and control from experience. Furthermore, RL agents can benefit from self-play in a competitive setting, such as air hockey, where they can discover potential weaknesses in their own behavior and develop better strategies to overcome them. That's why we have decided to go with RL. Both model-free and model-based approaches share qualities that might make them suitable for this task. However, our investigation is purposefully limited to model-based RL due to its perceived sample efficiency, which also makes it more suitable for the kind of applications I explore in my research. We decided to employ Dreamer v3 by Danija Hefna et al. Due to its demonstrated capacity for solving various tasks in diverse domains. At its core, Dreamer v3 learns three components, being the role model, actor, and critic. All of these are optimized concurrently during the training, while the actor and critic leverage the generative capabilities of the role model to optimize their networks from imaging sequences. This aspect of the line of work the Dreamer v3 builds upon makes it therefore suitable for the task of playing air hockey, because actions can be sampled quickly from a lean agent, which makes the inference much faster compared to using the role model directly to do online planning. Furthermore, I must say that Dreamer v3 works quite well out of the box without any hyperparameter tuning, which is always welcome to see. Now, coming to how we formulate the task, beginning with the action space. Below you can see our agent playing against the baseline while indicating the actions it takes. Since the entire game of air hockey takes place within a planar surface of the table, we provide our agents with access to the continuous actions in the Cartesian plane, expressed as the absolute target position of the mallet. These high-level actions are then mapped into lower-level joint space commands using the inverse Jacobian method, while maintaining the desired height of the mallet above the table. Of course, the dynamic feasibility of the resulting motion is ensured by clipping the joint displacements based on the velocity limits of the joints. Observation space of the agent is formed through a set of low-dimensional environment states that are accessible to the participants. Information about the position and manipulability of the controlled robot is captured by its joint positions and the planar position of its mallet, which is also observed for the robot of the opponent. The state of the puck is similarly observed through its planar position, but also its orientation. And finally, we also include a timer relevant for the fall detection mechanism of the environment. We employ observation stacking as a simple method to provide additional temporal information about the environment dynamics. In this way, consecutive observations of the selected states are stacked together and used as a single observation. We do this especially for the position of the puck that is considered of great importance for the problem, and it also suffers from the loss of tracking during the evaluation. Strictly speaking, observation stacking should not be necessarily with Dreamer, because the actor already benefits from the Markovian representation learned by the recurrent role model. However, no negative impact on the performance of our agents was observed by incorporating observation stacking, so we decided to keep it in the implementation. The behavior of our agents is reinforced through simple sparse reward signals that correspond to the positive event of scoring a goal and negative events for receiving a goal and causing a fault. These events correspond to the game score and should therefore provide clear reinforcement without introducing potential biases from integrated reward shaping. With small modifications to the reward function, it is possible to reinforce the behavior of agents towards different strategies. We experimented with 3 slightly different configurations for aggressive, balanced, and defensive playstyle. The balanced strategy was used by default and is designed to encourage the player to score goals while defending their own side of the table. The aggressive strategy resulted in more risky behavior, which we further incentivized by softening joint velocity limits. Agents following the defensive strategy do not receive any rewards for scoring a goal, which means that they are solely incentivized to defend their goal against the opponent. And as you can see, this actually resulted in an exploitative behavior where the agent would focus on getting the puck stuck in the middle of the table to prevent the opponent from ever touching it. The initial idea behind learning multiple strategies was to combine them into a single ensemble that dynamically selects one of the 3 agents based on the current score of the match. However, our implementation of this approach did not show any significant benefits over just using the balanced strategy. Regardless, we still use the concept of multiple strategies with self-play, which I will return to in a moment. Self-play is the last piece of the puzzle of our approach. Although a baseline agent is provided by the organizers, training solely against it would result in a policy effective only against the specific opponent. Therefore, we employ a form of fictitious self-play to iteratively discover more robust strategies during the training. In this way, our agents are trained against previous policies that are uniformly sampled from a pool of opponents at the beginning of each episode. This pool begins with the baseline agent and is gradually expanded with a new model while being limited to a total of 25 opponents. And as I mentioned before, the strategies from previous slide are also incorporated into self-play. First, 3 agents following the 3 strategies are trained separately using their own opponent pools. Once these agents begin to exhibit stable behavior, their training is terminated while keeping a history of checkpoints for their models. Subsequently, a new agent following the balance strategy is trained from scratch, but this time the opponent pool is pre-filled with checkpoints for each strategy from the previously trained agents. Here you can see an agent being trained against aggressive opponent as well as the defensive opponent. This forces the new agent to be immediately exposed to a diverse pool of advanced opponents, which should reduce the likelihood of the world model overfitting at the beginning of the training. Talking about training, we used a model with around 10 million learnable parameters, out of which about 1 million is used by the actor. With this model, the mean inference time of our agent was tested to be 5.2 milliseconds on the CPU of the evaluation server, which is well within the computational requirements of the challenge and leaves plenty of room for improvements. As for the training process itself, we employed 10 parallel environment workers to accelerate the training and provide diverse experience for agents. Such diversity is further improved through environment disturbances together with observation and action noise applied to the agent. Here is a learning curve of an agent following the balanced strategy throughout its training for 100 million environment steps, which is equivalent to about 7 days of real-world training. Although it might seem that the performance of the agent stagnates after about 50 million steps, the performance against the baseline agent continues to improve. To study the effect of self-play, we train another agent that is matched only against the baseline for the entirety of its training. This new agent is capable of acquiring a policy that is reliable against the baseline agent. However, when matched against the agent trained with self-play, it loses significantly. This indicates that self-play is indeed essential in this setting to enable agents to generalize to novel opponents. Without it, opponents are very prone to overfitting. To briefly touch upon the sim-tutorial aspect of the challenge, I will highlight 2 primary difficulties that were encountered with the deployment of our agent on the real robot. First of all, there are some safety concerns to be addressed. The submitted policy is based solely on sparse rewards and does not consider any constraints. This is noticeable even in the simulation, where it is clear that the policy is very chaotic and rapid changes in acceleration result in jerky motion of the robots. To mitigate this issue, we applied a simple filtering at the action level to smoothen the joint motion of the robot while also reducing joint velocity limits. This helped to some extent, but it also made the agent less responsive by introducing latency into its actions. The reality gap appears to be relatively small from the perspective of the agents due to the use of state observations and high-level actions. However, there are some discrepancies in the environment dynamics that might affect the performance of the world model. One such example is the effect of angular velocity on the puck bouncing off the walls. In simulation, this effect is quite small, but in the real world, the puck bouncing off the walls results in different dynamics that are not captured by the world model. To conclude, there are several lessons that I learned throughout participation. When it comes to the primary challenges, the aforementioned safety concerns need to be addressed. The policy should be more deterministic, and the continuity of the motion shall be enforced at the level of the policy itself through some objectives or constraints. Similarly, generalization remains an open challenge. Although self-play has proved to be essential, it was not sufficient to make our agent robust to novel opponents. However, this is to a large extent also because of all the great agents that were developed by the other participating teams. When it comes to potential future directions that might be worth investigating, continual learning for quick adaptation of agents to current opponents might become increasingly more beneficial for complex competitive domains. Another topic of interest might be the incorporation of self-play directly into the imagination present within Dreamer to further enhance the learning process. Thank you for listening, and many thanks to the organizers of the challenge for providing this great opportunity to learn and explore new ideas.